today I'm going to tell you the most important things you need to know about nuclear fusion, and where things stand and where they might go in the future. So in honor of this, I have my atom earrings on because we are harnessing the power of the atom with nuclear fusion. And I've also got a futuristic car behind me that is powered by Mr. Fusion. So let's dig in and learn a little bit more about fusion. So nuclear fusion is making use of the energy that's created when we squeeze two molecules together. Squeezing two molecules together to form a new larger molecule releases energy, lots of energy. This is the energy that we're using in the fusion reaction. This is different from nuclear fission. Nuclear fission is where we take a large atom like uranium and it's dividing it, we're separating it, and that also releases a lot of energy and makes two smaller atoms. Commercially, what we're using in nuclear energy is nuclear fission. We do not do nuclear fusion commercially. It is all in the research stage at this point, but we'll talk about where things stand. The excitement about nuclear fusion and some of the differences from nuclear fission are really important. So, like nuclear fusion is a carbon-free resource. It is extremely energy dense. It's actually even more energy dense than nuclear fission. And it has a fuel that is really abundant. We're typically using isotopes of hydrogen. We have lots of sources of hydrogen on the planet, including water. There's no radioactive waste when we're doing nuclear fusion. So that's a big key difference with nuclear fission. And like fission, there's no air emissions. So a lot of promise with nuclear fusion and its attributes. But it's a challenge. So nuclear fusion is occurring naturally and powering a lot of our energy systems already in the sun. That is what's generating the energy in the sun. The sun uses a gravitational confinement to force these atoms to fuse together. You have to overcome this Coulomb barrier that keeps these positive charges apart in order to get them to fuse together and release all of that energy. So you need a lot of pressure or temperature energy you put in order to make the fusion reaction happen. So that's hard to do on Earth. Sun's doing it all the time, but here on Earth, we have to do it a little bit differently. We can't use gravitational confinement. We can't reproduce the gravity of the sun on Earth. So we have to figure out other ways to confine and provide enough heat and pressure for fusion reactions to happen, for you to overcome that Coulomb barrier and release all of that energy. Two big systems that we do for fusion on Earth are inertial confinement and magnetic confinement. Those have kind of received the most research. But what we're trying to do here is reach temperatures over 100 million degrees C, sometimes quite a bit more, like 500 million degrees C, and create a plasma. That plasma is too hot to touch any material that exists on Earth. So we have to contain it in a way where it's not touching anything. And that's where we get to this inertial or magnetic confinement systems. We need a reaction that lasts long enough to produce useful energy. So we're getting more energy out than we're putting in. And we need to use that energy to create electricity. So all of these are challenges in making fusion actually be a productive energy resource for our energy systems. The cost has been really high for fusion research, but a lot of progress is being made. So what are these two most researched fusion approaches, the confinement approaches? One is inertial confinement, where you really have a small pellet of your fuel, so your hydrogen atoms, and you shoot lasers at it. And you can get very high densities of energy in a small space. So you get high plasma density, high temperature plasma, but pretty short confinement. So nanoseconds on that. For magnetic confinement fusion, this is another highly researched type of system. You can have longer confinement. You can have a relatively lower temperature plasma. They're both really hot and lower plasma density. But that magnetic confinement is able to keep the plasma away from the walls so you're not melting the confinement system while you have that fusion reaction taking place. The fusion reaction that is most studied and probably has the highest potential is with these isotopes of hydrogen, deuterium and tritium, and squeezing those together. And so what I'm showing you here is a fusion cross-section, but the takeaway is really that we can get a higher fusion probability at a lower kinetic energy that's required than some of our other reactions. And so you can imagine that this makes it easier to make that reaction happen And we have a lot of hydrogen isotopes that we can harvest on Earth. So fusion's main path to producing power is the same way that we produce power with a lot of different energy resources. And that's to produce energy that will boil water to create steam to turn a turbine and create electricity. This is just one design, but there are other designs. But basically, that's how we're harnessing that heat to produce productive energy in these systems. There is, in theory, ways of making electricity directly from fusion, but that is pretty under-researched at this point and is just theoretical. So what are the progress? We've made huge progress just in the last few years on nuclear fusion. So a big achievement was when the National Ignition Facility, that's in Livermore, California, at the National Lab, achieved the first scientific breakthrough in nuclear fusion. So what that means is this is the first time that there was actually more power released than was injected into the fusion reaction. Now, the National Ignition Facility is one of those inertial confinements. So they actually have a pellet with lots of lasers being pointed at that pellet, but they got more energy out of the reaction than they put in. That's scientific breakthrough. And you can see they've continued to make progress at scientific breakthrough, more and more energy coming out than is going in. We still have not achieved what's called engineering breakthrough or facility breakthrough. That's where we would have more energy out than was put into the whole engineering system or into the whole facility. So in this case, for example, there's still a lot of energy that went into powering the lasers to produce the energy that actually was in the pellet. We're still putting a lot more energy into the lasers to produce that reaction than we're getting out. But it is a huge breakthrough, and a lot of progress is continuing to be made in terms of getting a greater and greater Q value closer to engineering and facility breakthrough. A lot of funding has gone into fusion for over the years. Much of that has been in the public sector. This is just giving you a sense of the kind of the landscape of public sector research that's gone on. But private funding has really been where we've seen a lot of growth in the investment in fusion reactions. So the number of companies and the amount of funding going in are both growing. And there's a lot of new designs that come along with the startup realm and that private funding. So the two confinement methods, the magnetic and inertial confinement, are still very heavily researched, both public and private, but we're seeing a lot of other designs coming out of the private sector. So big picture, the good news is that we've made progress. There's a lot of demand and a lot of interest in this area, so a lot of funding and innovation going on. Bad news is that we still have a lot of scientific and engineering challenges associated with fusion. And so as we see progress on that, we'll see where fusion takes us. If you want to know more about energy fusion, please check out our fusion webpage and the full lecture if you want to hear more from our guest speaker on this topic, Clea Colster, who actually works in the private sector, investing in a lot of these new fusion energy startups. And so she has a lot of experience in what's happening kind of at the edge of the private sector and how things are developing and growing. So great insights there if you want to check it out. And of course, if you want to just learn more about energy topics, check out our monthly energy spotlight.